The animations and game loops we create using Rico's animation frame have a slightly big problem going for them. That problem is consistency. They don't always run at the speed at which either they're advertised or that we think they're going to be running at. They run at whatever speed the browser decides is appropriate for them to run at, which means different people on different browsers, or maybe even the same person at different times of the day, will see our animations and game loops running at different rates. Here's what is horribly problematic. Well, first of all, it's problematic because our browsers are horribly inconsistent and we don't like inconsistency. But imagine you're looking at animation. For some users, let's say a user on a very high frame rate device like a modern phone or a gaming monitor or so on, will see an animation running much faster than someone who's running on a more traditional display that runs at 60 Hertz or 60 frames a second. So here's an example where a blue ball is moving twice as fast for users on more higher end devices than there are on users running on a normal 60 Hertz kind of a display. So animations aside, this also impacts games. So here's a classic shot of Space Invaders. You can see it's just running at the top at a normal speed. Let's say I'm running this same game on a device that runs at 120 frames a second. And you can imagine now the difference in behavior and speed and expectation. You don't want this. It's one thing to say that, yeah, this animation is running a little fast, it's passive, runs in the background. It may maybe look nicer in some cases, but when you're playing something interactive like a game, you can see the difficulty is much different. On this screen, it's more manageable. I can see the characters, I'm moving slowly, I'm timing my shots, less mental strain. Here, the game is running on like super advanced mode on expert level, which is fine, that's what you want. But ideally though, you want to make sure that all the people who are playing this game have a consistent speed to compare themselves against. So that's also not very desirable behavior. And here's some reasons for why we have this inconsistency. Number one, and probably the biggest, is varying screen refresh rates. We have back in the day, our screens were pretty much fixed at 60 Hertz. We didn't have anything that was faster, and that was considered good enough. But as our devices have gotten more powerful, as our mobile devices have gotten more powerful, as our monitors start having increased refresh rates because games are smoother, input time is decreased, and so on, the screen refresh rates vary. You have 60 Hertz, 75 Hertz, 120 Hertz, even 240 Hertz for some of the more up and coming screens, like even like AR, VR kind of glasses, where the screen rate is ridiculously high. And so that's one big reason for why animations and games might be running at different speeds. The other 2, 3, 4, and 5, they're important and they also play a pretty critical role. The browser sometimes is too busy doing something more important, where replay takes lower priority. Imagine you're trying to sort a list of 1 million items. At that point, the bulk of your time is going to be spent by the browser getting that items sorted, less so on making sure the animations are running smoothly. Number 3 is the browser's minimize, or the browser tab loses focus. This happens all the time, and as a way of optimizing for battery and CPU, many browsers decide to stop all animation loops, which means that if someone was playing a game, tapped away to something else, and came back, the game would have basically paused at whatever state they were in, which may be desirable, may not be, but again, inconsistent. Number 4, the device is optimizing for battery CPU and change the speed dynamically. We can kind of see this sometimes when we are plugging in our device and using it, and we unplug it, we can see the screen dim a bit. Some of the superfluous animations on our device might be getting a little bit more muted, things like that. And last, some browsers, like Safari, don't support high refresh rates. You might be on a cutting-edge device with all the latest bells and whistles, but the browser artificially throttles you to run at a particular speed, which means that we need to account for that to ensure that people who are viewing something that you created in Safari, in Chrome, in Firefox, in Edge, and all the other browsers out there have an experience that is very, very consistent. And so the gist of it is this. The reasons for all these consistencies is the time elapsed between each request animation frame call varies. This is what is inconsistent. That's a technical answer for what all these problems are that we're trying to see here. So let's talk about how we're going to solve this. And we're going to solve it using an approach that is very common in the industry, common across animations, common across games. It's known as a delta time approach. But to explain delta time, if I just were to explain to you right now, you're going to be like overwhelmed by the complexity and the horribleness of how I'm going to explain it. So I'm going to start off by setting the stage, and we're going to talk about a dinosaur named Bob. Bob's a T-Rex, and he is just happens to be doing T-Rexy things, walking, feeding on things, and whatever else dinosaurs do. Now, the code we have is this. Bob is animating. Bob is moving from the right side of the screen to the left side of the screen. And the way the code looks for Bob right now is this. We have a variable called Bob position that determines the position Bob is at any given time. And we have an animation loop. And this animation loop is powered by request animation frame. It takes a timestamp as an argument, as all request animation frame loops are capable of doing. And with each frame tick, each call of animation loop, we are moving Bob's position by 5. Minus equals 5. So every time the animation loop function is called, Bob position variable, that variable's value is decreased by 5. Straightforward. Now the challenge, and here's what happens, is this. So each time request animation frame is called, Bob is moved by 5 pixels. We're on a 60 Hz screen, which means that over a period of a second, our refresh rate is 60 times a second, which means that request animation frame is also called 60 times in 1 second. That means over each call of request animation frame, we're moving our Bob by 5. That means we're moving by 300 pixels every second. So the first second, 300 pixels of Bob is moved. Second, 300 pixels, and so on. That is what we see on a 60 Hz screen. Now, let's say we're on a 120 Hz screen. This means that every second, our request animation frame is called 120 times. That means that the same code we saw before, where we're moving Bob by 5 pixels each time the request animation frame is called, in this case, because we're being called 120 times a second, Bob will have moved 600 pixels, almost double that of what he would have moved on a 60 Hz screen. This is the problem that we really want to solve. It should not matter what kind of screen I'm on. I could be on a 120 Hz screen, I could be on a 60 Hz screen, I could be on a 10 Hz screen, for all that no. But what really should mean is that Bob should move a fixed amount based on what I think is the appropriate amount as the animator or game developer. And so what just happened is this. After 1 second, Bob moved a different distance in the 60 Hz case compared to the 120 Hz case. And this is exactly the kind of situation we want to avoid. Every user who views this animation should see Bob moving the same distance at the end of 1 second. That is our goal. And not just animation, of course, even with games. And so the first question is, what is the correct answer here? What do you want to default to? And if you want to think about how far should Bob have moved at the end of 1 second, there are many answers here, but the one that I think almost everybody will agree with is we want to default to an expected frame rate of 60 Hz or 60 frames a second. And that is because for so long, it's almost a minimum that modern devices need to support in order to be considered capable of displaying very fluid, very tear-free animations. And so therefore we can optimize for whatever needs to happen to ensure we get a 60 Hz, 60 frames per second solution. So that way we are standardizing on a speed that all users will see. Now, besides just the frame rate we want to target, there are 3 things that we have kind of the levers to control. And we're going to go into more detail on at least 2 of these. First one is delta time. This is a term you might see very frequently. If not, please etch this into your memory. It's a good term to keep always at the top of your hat. It's the elapsed time between each request animation frame call. That means that on a 60 Hz screen, request animation frame is called 60 times a second. There's a time between each of those calls. That time is known as the delta time, and it varies. It varies based on the speed at which request animation frame is called, which goes back to the 5 things that influence the speed of it, which is refresh rate, what your browser is doing, how much battery and CPU are being used, all those things. The second is a target frame interval. This is the desired time between each frame update determined by the target frame rate you want to achieve, which we saw a second ago is around 60 frames a second. The last one is the rate of change. All of our animations have code that changes the value by an amount at every frame tick. In the case of Bob, we decided to move him left by 5 pixels every frame tick. Different animations, different things you're trying to animate and move around will have different values, but they will just generically call that the rate of change. Now let's talk about delta time in particular. This is the time between each request animation frame call. So on a 60 Hz screen, the value is going to be 1 over 60 or 16.667 milliseconds. Or on a 120 Hz screen, it'll be 1 over 120, which is 8.333 milliseconds. Now, this is ideal conditions. this number will vary based on what our browser is doing and whether it has to speed up or throttle the speed as necessary. So on average, in an ideal world, it'll be 1 over 60 on a 60 hertz screen, 1 over 120 on a 120 hertz screen, 1 over 75 on a 75 hertz screen, and so on. And it will be changing based on each frame tick. The one that won't be changing, unless we try to change it, is the target frame interval. We typically said that we want to have a frame rate of 60 frames a second. So if you want 60 frames a second, what would the time between each frame call be? It'll be 1 over 60, which happens to be the same as the value for 60 hertz. That would be 16.667 milliseconds. And it sounds familiar, and some of these numbers get confusing because they're so common across all of them. 60 hertz you'll see all the time, 120 hertz you'll see all the time between all of the various values you're trying to do. So a big part of making sense of all this is keeping track of the same number used in different contexts. So let's get back to Bob. We talked about the delta time, the target frame interval. Let's go back to Bob again. So using the terminology we just saw, what we really want to do is optimize for 60 frames a second. So in this case, our screen is 60 hertz. We want to go for 60 frames a second, which means our frame interval and our delta time are the same. They're both going to be 16.667 milliseconds. So Bob moves exactly 300 pixels over a period of 1 second. Life is great. In this case, things are a little different. Our delta time is 1 over 120, or in the slide we saw earlier, 8.333 milliseconds. And our target frame rate, the interval we want, is 1 over 60, or 16.667 milliseconds, which means that in this case, even though our frame rate is 60, our request animation frame is called double that, from every 8.33 milliseconds, and so therefore Bob moved 600 pixels. So we're seeing the same thing we saw a few moments ago. We're just adding more terminology to make the sound what is going to match the code that we're going to be looking at. So here is the problem. All of this is here to kind of explain to where we are right now. Our request animation frame has a delta time of 8.33 milliseconds in the 120 hertz case, which is, what we talked about earlier, double that of our interval value of 16.67 milliseconds. And this is why Bob has moved so much in the 120 hertz case, whereas he only moved 300 pixels in the 60 hertz case. So how do we fix this? So the way we fix it is by figuring out a way to adjust the rate of change, the third value in the three things that we control. So for a 120 hertz situation, we know that Bob has moved at a delta time of double the 60 frames a second approach. What if we decided at that point saying, you know what, we can't change the frame rate, so we can't change the delta time on all these devices. That'll be determined by the device and what it's doing. We can specify the frame rate. Can we use those two values to adjust the speed at which Bob is running? So in the 120 hertz case, what if we decide to increment Bob's position not by 5 pixels, but by exactly half, by 2.5 pixels instead? In that case, we'll get the same result. After 1 second, 120 times 2.5 is, you guessed it, 300 pixels, which is the same as 5 times 60, which is exactly the 300 pixels he would have moved in a 60 hertz case. So how can we generalize this? How can we use this knowledge to adjust the speed at which our animation and our game loops run so they're consistent across all users, all devices? And that's where the topic of the delta time multiplier comes in. The delta time multiplier is the delta time divided by the frame interval. In many cases, it'll be 1. In some cases, it might be 0.5. Other cases, it might be 2. It could be varying between like 0.999 and so on. This is something that will be dynamically calculated to ensure our animation stays smooth all the time. And so if we went back to some really rough pseudocode, let's just imagine, for example, that we took the same code we saw earlier of Bob's position. We just added a few extra lines here. We have a variable called delta time. And that one, we say that, let's say we're in a 60, let's say we want to target is essentially 120 frames a second, but our delta time, we're on a 60 hertz device, and so we're going to be having our code run every delta time will be 1 over 60, which is 16.667. Our frame interval though will be much higher because we want to have 120 frames a second as part of our game, so that people on high-end devices get the best experience. People on lower-end devices can still play it in a consistent way, but it won't be as smooth. And so our frame interval is 1 over 120, 8.333. If you're noticing this inconsistency, we're swooping things around. Before it was a case where we are on a slow device and we want to have the animations being viewed on a high-end device. In this case, we're flipping things around. We want our animation to run at very high frame rates and we're on a low-end device. And so notice here that I have a delta time multiplier and we're dividing delta time by frame interval. And that value is being fed to the area where we're increasing Bob's position by minus equals delta time multiplier times 5. In this case, what this means is that it'll be multiplied by 2, so that way on a low-end device, every time the frame interval is kicked in, or every time delta time runs, we move 10 pixels each time. Whereas on a high-end device, it'll be 5, but because of how the time normalizes, it'll all be the same thing. Now, this will all make a little bit more sense when we look at this example in code. So I'm going to go into VS Code, and so here I have an example, and here we also have Bob currently moving in a, I didn't even save that. You can see Bob currently moving properly. He's moving from right to left, and we're moving him exactly at a value of minus or equals 5, which is more of the code that we saw earlier. And the way he's moving is that we're setting the property called xposition on Bob itself, and that value is specified in our CSS. By default, it's set to 0 pixels, and it maps to a transform where the position value is used to translate his position from right to left. And so that's how we map between a changing value in our JavaScript to a changing visual on screen powered by CSS. All right, so now that we know this, we know that the approach we have right now is going to result in Bob moving at different speeds on different devices. Right now, I'm on a 60 Hertz screen, which means that every 1 second, Bob moves 300 pixels, like we discussed earlier. But if I was on a 120 Hertz screen, Bob would move much further. Let's go ahead and fix that. So the first thing I'm going to do, let me first make this much smaller. Like, I don't think we need this much space to see Bob moving from left to right. Let's see, can I even resize it? Yes. Okay, let me make this font size even bigger. All right. So what I'm going to do first is declare a few variables. I'm going to let frames per second. I'm going to say it's equal to 60. This is the frame rate that we ultimately want to target. And then I'm going to say let frame interval equals 1000 divided by frames per second. This ultimately ends up being 16.66667, but instead of hard coding that value, we'll let JavaScript deal with numbers the way it does it best. And now let delta time multiplier. Now I'm just going to leave it as just 1. This is just a value I'm using. I'm initializing it to 1. It'll change in real time, so we'll start with 1 as a safe value, and let delta time equals 0. Now both these variables will be changing, so I'm not expecting it to be 0, nor am I expecting it to be 1. In fact, it's also fair to actually make this easier by saying const frames per second and const frame interval equals 10, just to kind of signal that I do not intend for these values to be changing. And then let me then get one more value of let previous time equals performance.now. A big part of this effect will be to ensure we know what the time has elapsed between each call of request animation frame. All right, let me just refresh the page to make sure I didn't do anything silly here. Bring up the console, like my usual things, and yep, so far so good. No errors, we're fine. Okay, so now here I am in my animation loop. So the first thing I'm going to do is specify delta time equals current time minus previous time. And this is because we know that the animation loop gets a high precision timestamp, and that timestamp needs to be reconciled with the previous time that we had defined earlier. So now each time the animation is called, we can know how much time has elapsed between each call of request animation frame. So we're just showing the difference between the previous call and the current call and storing that as our delta time. And with this, the delta time multiplier becomes, in this case, delta time divided by frame interval. And that is really the gist of the main calculations that we need to do. And once we have that, it's time to make sure we use the delta time multiplier by where we're adjusting the position of Bob, adjusting the rate of change. So minus 5 times delta time multiplier. So at each frame tick, whatever this value is, will influence by how much Bob is moved at each frame tick. But the idea is that our goal is to always match what the value would be by what frames per second that we have currently defined. Let me refresh this page. I can see that Bob is getting really, really fast, and almost ridiculously fast at this point. And so what's going on here? And the reason is this. Previous time needs to be reset after we are done with this here. So I'm going to do previous time equals current time, just so we now set the old value or as our new value, or vice versa, the new value as our old value, to make these calculations work appropriately. So now you can see Bob continues to move as he would normally, but the difference is if I was doing this on a high frame rate device, the speed at which Bob is moving visually will look exactly the same. So there'll be no more inconsistencies between Bob moving too fast in some cases, too slow in some cases, and so on. And that's really all that it takes to add the delta time multiplier to how we create our animations. Now, the thing I want to clarify is that there's one more approach that we can use. Instead of using the delta time that dynamically changes the rate of how we're animating, the speed at which we're animating at each frame tick, we can fix the frame rate. We can say, you know what, I want my animation or my game loop to run at 15 frames a second, and do a different approach where we're using the time to force a frame rate that we want. There's also an approach that you can use. It's not my preferred approach. I don't like it, but in the article, which I'll link to below, where I talk about this exact same topic in written form, I do cover how to fix the frame rate. So if you are curious to check that out, do take a look at that just so you're aware of what to do here. And so there you have it. A very quick overview. Actually, I wouldn't say it was quick. I think it was a little bit more on the long side of how to ensure we can have our game loops and animations run at a consistent speed. Now, many tutorials, many videos that I talk about or you'll run into are often optional. It's recommended, but if you don't follow it, you're okay. This is one of those rare moments where you absolutely have to have this code, this way of either fixing the frame rate, like I discussed in the article, or like we talked about in this video, how to ensure we're using the delta time multiplier and the delta time approach to adjust the rate at which we are animating our content. Because if you don't do this, different users will see different speeds of your animation, different speeds of your game running, which can drastically affect the user experience. You don't want to give an advantage to someone on a very slow device, nor do you want to penalize someone on a very fast device. And so this is something that you need to follow, and subsequent animations that I talk about that use Recursive Animation Frame, you'll start to see me using this delta time approach in all of the animations. No matter how simple or trivial they may be, they will all include this. And so with that, if you have any questions on any part of what we saw, post in the forums at redcurve.com, where I and others will be happy to help you out. Subscribe to my newsletter, where I talk about animation and other front-end topics and things that are a little bit deeper on the business side of things, the design side of things, and the technology side of things. And follow me on Twitter if you want bite-sized updates on various things that I'm fiddling with, or just want to share interesting topics that I am currently reading. And lastly, if you like my style of explaining things, if you like to read content on the screen, you may also enjoy the books that I've written. Now, I've written a handful of books on various front-end topics, available at paperback and digital Kindle editions. So check those out if that also fits your fancy. And they also make really great gifts for both your friends and enemies. How about that? Talk to you all later.